So I want to discuss now what will happen if we terminate a transmission line. So up to now we always considered that the transmission line has an infinite extension, and we saw that we have a possible wave traveling, for example, in the positive z direction. So if I assume that we have a wave traveling in the positive z direction, we will have here always the voltage u of z, and in this point the current I of z, and the ratio of the voltage over the current u of z over I of z will always be equal to Zc, the characteristic impedance of the transmission line. That our transmission line is described by the two parameters Zc, and the wave propagation is described by gamma. And here we have the z coordinate of, for example. And what I will discuss now is that I consider the same transmission line here, which is described by the same parameters Zc and gamma, but instead of an infinite transmission line, I now assume that we terminate our transmission line at a certain point z equal to the length of the transmission line, and I will assume now that we connect here a resistor at the end of the transmission line, and we will choose the resistance of the resistor equal to Zc. So if I consider the same wave now traveling in the positive z direction, of course, then always the ratio of voltage and current is given as before by the ratio is given by the characteristic impedance. But what will happen now if this wave comes to the point L? So we will have here U of L, which is a voltage at the length L, and we also have here the current E of L. And since we use as the resistor the value which is equal to Zc, also the ratio of U of L over I of L at that point is given by the same ratio, or is given by also by the characteristic impedance Zc. So in principle there is no difference between assuming a transmission line of infinite extension and a transmission line with infinite extension, but which is terminated in Zc, because essentially the wave does not notice the difference. So we can conclude, if a transmission line is terminated in its characteristic impedance Zc, we can conclude no reflections will occur. On the other hand, if we now think on the point that we terminate the transmission line in an arbitrary impedance, then of course reflections will occur, and that we will discuss in the next step. I now want to discuss the case where we have a a transmission line which is described by its characteristic impedance ZC and gamma, but now I assume that the transmission line is terminated in an arbitrary load impedance ZL. In the step before, we discussed as soon as we terminate the transmission line in its characteristic impedance, no reflection will occur. But if I have now the transmission line terminated in an arbitrary load impedance, of course, then we will have reflection. This means we will have an incident wave, I call it incident wave UE of Z, which will travel in the direction of our load impedance. But since the load impedance is not equal to the characteristic impedance, we will also have a voltage wave, I will call the reverse traveling voltage UR of Z, which will travel down the transmission line here. And we know from our general theory that we can describe UE of Z, the incident wave, as a constant I will also call UE, but the functional dependence will be given by the exponential function of minus gamma times Z. So we know that this expression describes a wave which travels in the positive Z direction. And this wave here, this reverse traveling wave, will be given by UR of Z. It also will be a constant UR, but again we assume the functional dependence. It's also given by the exponential function, but now with a positive sign. Gamma times Z. So in this case we'll have a certain a different functional dependence, here the positive sign and here the negative sign. And now we can define the reflection coefficient which I see at an arbitrary point into the transmission line. I will just call R of Z, and it will be defined as a ratio of the two voltages of the reverse traveling voltage UR of Z divided by UE of Z. So this is the arbitrary definition, or this is a reflection coefficient at an arbitrary point. So we can conclude then, for example, this to be the load reflection coefficient R of L, which then will be the voltage UR of L divided by UE of L. And the same we can define here for Z equal to 0. We will call it the input reflection coefficient, or in. But in our case it will be then UR of 0 divided by U in, or UE of 0. So these are the two definitions, and for example we can now use this expression to calculate RL, which we sometimes also denote as RL, the reflection coefficient of our load. So we will get, for the reflection coefficient of our load, it will be equal to UR of L. So we use this expression. This is UR times the exponential function of plus gamma times L divided by UE times the exponential function of minus gamma times L. And we can rewrite this expression as UR over UE multiplied now times the exponential function of plus 2 gamma times L. So we see here, for example, we have the ratio of UR to over UE, and this, if you insert z equal to 0, then you get UE here. If you insert here z equal to 0, you get UR. So you see that the input reflection coefficient is equal to this term. This is our input reflection coefficient. Of course, we can in principle now rearrange this equation to the fact that we say in the input reflection coefficient will be equal to the load reflection coefficient times the exponential function of minus 2 gamma times L. So what we have here is in principle a nice equation which relates the output reflection coefficient or the reflection coefficient of our load to the input reflection coefficient. So we will now have a look on the transformation of the reflection coefficient along the transmission line in more detail. What we're discussing here is we consider a transmission line having a characteristic impedance ZC and gamma, and we assume that this transmission line is terminated in a load impedance which is not equal to ZC. Then we will have at the end of the reflection of the transmission line will have a reflection due to the load ZL, and we call it RL. This is a reflection coefficient which occurs at this point on the transmission line. And we, in a step before, we saw that this is in principle now the transformation law. That means we have here to account for gamma, which is normally given by gamma is alpha plus J beta. We have here the attenuation and the phase propagation constant. Of course, we can split this expression into the two terms, and we can see that we have Rin then is equal to RL, and we have two terms, exponential function of minus 2 times alpha times L times the exponential function of minus J 2 times beta L. And I will want to sketch this equation or the result of this equation in a R-plane, which means I assume here an R-plane. We have here the real part of R, and here we have J imaginary part of R. And of course now our load reflection coefficient here will show a certain value in this plane. This means I can draw it as an arrow in this plane. For example, I draw it like this. I assume this to be RL. And now we see that we have in principle two terms. Of course, this term will do a rotation to the reflection coefficient in clockwise direction. So I can in principle use a compass to do this transformation, this term will do a rotation in clockwise direction like this, where here occurs a certain angle, and the angle which here occurs will be 2 times beta L, or which would be equal to 4 pi L over lambda. This is the angle of rotation in clockwise direction, and here of course we will have a second term which will reduce the length of our reflection coefficient. This means we go into this region here, and if I have a look to the overall transformation, then this will be the composition of those. This will change the angle and this will change the length, so we will approximately have a transformation along this red line here, and the input reflection coefficient is then given by this arrow. This would be now our input reflection coefficient. So this diagram shows you how the transformation works. So as long as we have a lossless transmission line, we would only have a rotation, but if we have a transmission line with losses, also the reflection coefficient will become smaller at the input of the transmission line. I now want to deduce an expression which relates the reflection coefficient of the load to the load impedance itself. We saw that we have at the end, will have the voltage U of L, the voltage over the load, and the current into the load. Of course, we know that U of capital L is in principle the voltage at the total voltage of the wave at a certain length L, and of course we can we must remember that this is the incident voltage wave at this point plus the reflected voltage wave at this point, and of course this can be rewritten as UE of L times 1 plus UR of L over UE of L, which is in principle, or which is identical to the reflection coefficient L, R of L, which is identical to the load reflection coefficient, or we can say this is UE of L times 1 plus the load reflection coefficient R of L here. On the other hand, we also will have the current at this point, so I can write E of L will be equal to the current E at the point L, which is again a superposition of the two waves, the forward traveling wave, but we know that this is in principle UE of L divided by ZC. This is the current of the forward traveling wave, and we have to subtract here because the current of the reverse traveling wave will flow in the opposite direction. This will be UR of L divided by ZC, and this we can rewrite as Ze of L divided by Zc, and we will have here 1, and here occurs again minus UR of L divided by UE of L, which can be written as UE of L divided by Zc, and we have here now the expression 1 minus R of L. So we have two expressions here, E of L, one expression for the current into the load and into the arbitrary load, and one expression for the voltage. And of course we know that ZL, the load impedance, is nothing else but the ratio of the voltage U of L divided by I of L. And what you see here is, if I must divide this equation by this equation, of course UE of L will cancel out, and we will have that this is Zc times 1 plus R of L, and here we have 1 minus R of L. So we have here an expression where we have the load impedance Zc and R of L, and of course this is easy to resolve. So we can find for R of L, if we resolve for R of L, we will find that this is ZL minus Zc divided by ZL plus Zc. So we found now an expression. With the help of this expression, we can, for an arbitrary load impedance, we can calculate the reflection coefficient here. And I just want to discuss the one point. You see, as soon as the load impedance becomes equal to Zc, the reflection coefficient, or L, will be 0 and no reflections will occur, which we already deduced without all the mathematics we have had to use here. So I now want to deduce an expression which describes the voltage distribution along the transmission line. We know that the voltage U of Z will be the superposition of the two waves, so we can write that U of Z will be equal to the incident wave, or the forward traveling wave, times the exponential function of minus gamma times Z. And of course it will be the superposition, or will be added the voltage of the reverse traveling wave, or the reflected wave, times the exponential function of minus plus gamma times Z. So this gives in principle the voltage distribution along the transmission line. And what we can do is we can exclude this expression, so we can write this is equal to UE times the exponential function of minus gamma times Z. And we will have then here, this is 1 plus UR over UE times now the exponential function of plus gamma, we have here 2 of 2 gamma times Z. Of course, here we see this is the input reflection coefficient, Rn, and we know that the input reflection coefficient, Rn, is given by the reflection coefficient of the load times the exponential function of minus 2 gamma times L. Of course, this can be inserted here, and we will get then, this is UE times the exponential function of minus gamma times Z times 1 plus, now we can insert this expression here, and you will see here's a bracket missing, but then you will see that we can rewrite this as the load reflection coefficient times the exponential function of minus 2 gamma, and now we can rewrite here L minus Z. This is L minus Z. So of course now we have here the problem that gamma is a complex value and it will become too complicated to discuss. So I will use gamma going over of J beta, which means we will take a lossless TL, a lossless transmission line, so we only have to substitute gamma by J beta, and we will then have U of Z will be the incident voltage UE times the exponential function of minus J beta times Z times 1 plus RL times the exponential function of minus J2 times beta, and here we have L minus Z. And of course later on I will be only interested in the absolute value, so we can take the absolute value, which is identical to the amplitude, and if I take the absolute value of this, then this will be equal to 1, and we have to discuss the absolute value of this expression. So I can then say U of Z, this is the amplitude at a certain point in space, will be equal to the incident voltage wave times the absolute value of S, if I define this to be the complex value S. And in the next step we will give some graphical representation of this absolute value, and then we will discuss the voltage distribution along the transmission line. So now I want to discuss again the voltage distribution on a transmission line for the ratio of the amplitude at a certain point Z over UE of the amplitude of the incident voltage. We got this expression, and to understand this expression I sketched here a so-called S-plane, and we see that the S consists of two terms. One term is a 1 here, so we go first here, and then we have here of course an arbitrary load impedance, RL, and of course this arbitrary load impedance can have an arbitrary complex number, for example like this, RL, and you see here we have a second term, which as soon as Z becomes smaller than ZL, this means in this region here we have the length L, and as soon as Z becomes smaller as L, then you see we will have a rotation in clockwise direction, so that for an arbitrary load impedance, this RL will be rotated on a circle around the 1. So we will always get a high value and of course a low value. And now I want to discuss three different special cases. First I want to discuss the case of matching, which means we have RL is equal to 0, which corresponds to a matched transmission line, which again means that ZL in this case is equal to ZC. That means we will have no reflection, and as we have no reflections, of course, then there also cannot exist any interference, and RL is 0 here. So we essentially have all over the transmission line the ratio equal to 1, U of Z equal to UE is 1. This means we have, if you go along the transmission line, then you will have all over the transmission line, you will measure the same voltage. We will have no standing wave on our transmission line. And as a next point, I want to discuss the so-called short circuit, which means now I will assume that RL, the reflection coefficient, is -1. If we have -1, then we have a shorted TL, which again means that the load impedance is equal to 0. And you see, if RL is -1, then we will start in principle here. So we have 1, -1. We will start here, and again we go in clockwise direction. So we will start at 1, go to the 2 and go back. And you see now that at the end of the transmission line, due to the short circuit, there will be no voltage at all. So we will have here no voltage, and then of course, and if we come to this point, we will have double of the incident voltage, and then you will have no voltage again. And if you calculate this, it will show that you have a sinusoidal voltage distribution like this. Again, here you will have the maximum, and round about here the minimum. So you have a totally standing wave on the transmission line. This is one special case where we have a shorted transmission line. And the next I want to discuss with you is if I have RL equal to 1, then we have an open TL, which corresponds to ZL tending to infinity. Of course, if we have RL equal to 1, we start at 2, This means at the end of the transmission line we have 2 times of the incident voltage, and then we will have again a maximum of the voltage, 0 again, so, and it will almost look like this distribution, though of course here we will not have it 0, so it will look almost like this. So this is now the standing wave. So we can conclude we have 2 situations or 3 different situations. We have one which is called the match transmission line. In the case of the match transmission line, we would measure all over the transmission line the same voltage. No reflection will occur, and this means you can transmit your information perfectly over the transmission line. But if you have a shorted transmission line or an open transmission line, then you will have a totally standing wave on the transmission line. All the energy will be reflected back and no energy will be transported on the transmission line. So in between, if the absolute value of R is smaller than 1, then you will have a certain voltage distribution. That you will have a maximum voltage, and sometimes you will have a minimum voltage. And where the maximum and the minimum lies depends on the phase of the reflection coefficient. But another very important point is, as soon as you have a short circuit transmission line or an open circuit transmission line, you can measure the wavelengths on the transmission line as the distance between 2 minima, because the minima are very sharp, so you can measure this to get the wavelengths on a transmission line.